just put some stuff in here for these guys. Okay. All right. Yes?
Okay, that problem right there, is it all right that we form the 1 over A changes in inverse vector A plus B with the...
So what?
Formula with 1 over A times tangent with the inverse tangent of vector A plus B.
Okay, inverse tangent.
Well, I mean, like almost the same formula, but separately with the inverse. So that's...
But for this one, you want to use the inverse tangent?
I don't want to use the inverse tangent,
Okay.
the same formula. You know what I'm saying?
No, I don't know what you mean by we say it's the same formula.
Yeah, but why are you saying that square root of x squared minus 2 squared, that isn't the inverse tangent.
Right.
Yeah, right, okay. This one, I wouldn't sneak this one in for you guys on the test, but here's homework you could find out, and I think we had mentioned it in class, that the derivative of the sec inverse is this formula right here. So hopefully you can identify that with this problem here, you're gonna be needing to use that inverse function. That's on a homework, not on the test. So that wasn't the formula that I gave you on the sheet that you have to know for the test. Okay. All right. So what I want to point out with this is, and actually, comment here in class got me thinking about this, so I thought it over. I also conferred with somebody else too, just to make sure that my thinking wasn't crazy. And we do have to cover new material next week. I mean, we just can't have next week be the test, all right? So I think it's reasonable to say let's have the test be on Wednesday now rather than on Friday. You guys still have 5 more days, all right? It's not like I'm telling you on Monday that the test is going to be on Wednesday, all right? Yeah, Moha, what's going on?
We're doing a little bit of work on the wireless on the floor.
Yeah.
I know you're working in classes, but I just wasn't sure, like, if your laptop may drop wireless.
Oh, I see. But I'm okay here because I'm plugged in.
You're
All
okay.
right.
You're okay there. I just wanted to let you know if anyone has any phones that with the wireless.
Okay, thanks. Not Moha, Joe. Sorry.
I respond to it.
Okay. All right. So Monday, we are going to cover new material for that hour class. It's going to be that section 7.1 on integration by parts. Then on Wednesday, we're going to have the test. And then also on Wednesday, because the point of the take-home quiz and the homework is to help prepare you for the test. Turn in the homework and the take-home quiz on Wednesday instead of Friday. It's crazy to take the test and then do the take-home quiz and turn it in on Friday. You want to do that first. So therefore, all of that stuff that was due on Friday and that we're going to have on Friday is now on Wednesday. We all okay with that? Not necessarily we're okay with it, just that we understand. And then on Friday, we have the 2 hours on Friday. We'll be then going back to new material, section 7.2. Okay. All right, so Samuel said yes. Do you guys get what I printed? I typed in a whole bunch of stuff up there. The test is on Wednesday, the 11th of September. The homework that was due on Friday, this a week from today, is now also due on Wednesday, and the take-home quiz that was due a week from today is also due on Wednesday. All right? So everything's pushed back, okay? Pushed forward, not back. Also, the solutions to the practice set that I've given to you guys, that will be available to you. The full solutions will be available on Blackboard on Sunday afternoon, okay? So you can, so also that practice set. All right. Also, let's see, we can just, by the end of class, I want you to also, if you turn in homework number 2, you can just set it right there, over there. And also you guys, homework number 2 is due today also, so that needs to be handed in, okay? All right. Okay, so what we were looking at here was, we were on section 6.8, which is about this theorem or fact called L'Hopital's rule. So let me just write this down again on the reader here. So, L'Hopital's rule. Okay. If the limit of f of x is equal to 0 as x approaches some number a, and the limit of another function g of x is also equal to 0 as x approaches a, if those two conditions are met, or if this other set of conditions is met, or if the limit as x approaches a of f of x is either equal to plus or minus infinity, and the limit as x approaches a of g of x is also either plus or minus infinity, then the limit of the ratio f of x divided by g of x as x approaches a is going to be equal to the limit of the ratio of the derivatives, equals the limit of f prime of x over g prime of x as x approaches a. This first case where they both approach 0 is the 0 over 0 case. Yes, okay, the question was, can the rule be used when we have positive infinity over negative infinity? And yes, the rule can be used in that case, okay? Or negative infinity over negative infinity, all right? And then the second case here is our infinity plus or minus over plus or minus infinity case. Then we can apply the rule. But we have to have either of those two conditions satisfied. All right. So I did a few examples last time. I want to do a few more. So let's first of all look at the limit as x approaches infinity of ln of x divided by the square root of x. All right. Now we see here as x approaches infinity, the ln of x also goes to infinity. And as x goes to infinity, the square root of it also goes to infinity. So this is an infinity over infinity case. So we can use this rule. And instead of just keep writing down L'Hopital, I'm just going to say we can use the rule. All right. So let's look at the derivatives then. So this is going to equal the limit as x approaches infinity. Well, what's the derivative of the natural log? It is 1 over x. So we put that in the numerator. Now what's the derivative of the square root of x? Well, when we work that out, it's going to be 1/2 times x to the negative 1/2 power. Okay. All right, let's figure out what we've got here then. Let's look at the algebra with this. So this is the limit as x approaches infinity. Now what do we have here? This is, first of all, when you divide by 1/2, that's the same as multiplying by 2. All right, so we've got that. Now here I have x to the negative 1/2 in the denominator. Well, I can move that up to the numerator if I make it a positive 1/2 exponent. So the numerator then becomes 1 over x times x to the positive 1/2. And I've moved everything out of the denominator so I can just put it over 1. Well, what does this come out to be? Well, let's look at this. Limit as x approaches infinity of 2 times, okay, we have 1 over x times the square root of x. So that combines or simplifies to 1 over the square root of x. All right, now we look at, well, what is this limit? As x goes to infinity, this square root denominator also goes to infinity. So we get a really, really big number in the denominator, so that means that our limit here is going to be 0. And that's our answer. One application of L'Hopital's rule, yes? All right, you're just playing with me with the facial expressions. All right, good. I'm just kidding, sort of. All right. Now let's look at a second example here. I'll put this up here. And let's widen this a little bit. Without messing things up. Okay. All right. Are we okay with that first example? No? Yes? No? Susan's going. Jenna? Yes? That's basic college algebra or intermediate algebra. 1 over x to the negative 1/2 power. When you're flipping an exponent from either numerator or denominator to numerator or from numerator to denominator, you change the sign of the exponent. This is equal to x to the positive 1/2 power over 1. Okay. All righty. Let's get rid of that thing then. All right, let's look at our second example here then. What do we have? Let's find the limit as x approaches 0 of x over, the tan inverse of 4 times x. Okay, first of all, you always want to see, well, can I apply this rule? Well, obviously, when x goes to 0, the numerator is going to go to 0. All right? Now, what's the tan inverse of 4 times 0, or the tan inverse of 0? I.e., what angle has a tangent equal to 0? 0, exactly. The tangent of 0 is 0. So therefore, the tan inverse of 4x, that also goes to 0. All right. So therefore, we have a 0 over 0 case. That means we can apply the rule. All right. Okay, so let's do the derivative then. So this is going to be equal to the limit as x goes to 0. Well, the derivative of x on top, that's 1. All right. Now, what's the derivative of the tan? Let's go over here to the side of our paper. What's the derivative of the tan inverse of 4x? All right, the derivative of the tan inverse is 1 over 1 plus whatever this is squared. So that's going to be 16x squared. But we have to do the chain rule with this, times the derivative of 4x, which is 4. Everybody okay with that? All right, so over here on the denominator then, I have another fraction, or what's called a rational expression. It's going to be 4 divided by 1 plus 16x squared. All right. Now, let's then again use some algebra here. Whenever we divide something by a fraction expression, it's the same as multiplying it by the reciprocal. So this is equal to the limit as x approaches 0 of 4 over 1 plus 16x squared, the reciprocal, I'm sorry, yes, that's not the reciprocal. How about 1 plus 16x squared divided by 4, that's the reciprocal of the denominator, and then we have that 1 there. All right. Okay. So this is our new expression, and now let's plug in the 0 for the x, and what do we get? We get 1 plus 0 over 4 times 1, so our limit is what? 1 over 4. And that's our answer. One application of the rule, watch the algebra. Okay? Question on that example. Let's do a third one. And this one has a little bit of a different thing to it. I wanted to add this one in because it's one of the things that I ask you to remember on the formulas to remember sheet. So here we have it. The limit as x approaches 0 of x times 3 to the x power divided by 3 to the x minus 1. All right. Let's recall, shall we say, let's go down here and let's recall what the derivative of, say, 3 to the x equals. With this, we repeat the function, 3 to the x power, times. And then it's times the ln natural log of the base. So times the ln of 3. Right, so that is the derivative, of 3 to the x power. Notice, let me just say this, notice that if our base were the natural base e, it comes out to be, okay, we repeat the e to the x power function, but then we multiply it by the natural log of the base. Well, the ln of e is just equal to 1. So this is consistent with the other formula, because the derivative of e to the x is itself e to the x. All right, let's figure out what the top and bottom is here. This is going to be replace 0 for x with 0, 0 times 3 to the 0 power. Well, this is going to go to 0 as x heads to 0. The bottom part, let's look at the bottom. This is going to be 3 to the 0 power, which is 1. 1 minus 1 is 0. So the bottom also approaches 0. So we recognize that this is indeed a 0 over 0 case. So we can use the rule. All right, let's go way down here then. All right, so I need to do the derivative of the... Yes?
What's the derivative of x again?
The derivative of e to the x power is equal to e to the x.
I can't remember.
The number one? Here it is on the middle of page 2 here that's under the chain. Are you talking about our formula sheet? The derivative of a to the x is equal to a to the x times the natural log of x. What are you looking at? Just looking at... Let's see. It's not in there at all, you mean?
Yeah.
Okay. You might be looking at the wrong spot. But here, it's in the sheet here. I know we did cover it briefly. It's on the sheet. So trust me that we did mention it. Right? Okay. And it's in the middle of page 2 of this formula sheet. Okay, so we got 0 over 0. So this is, take the limit. Now let's do the derivative of the numerator and the derivative of the denominator. Now for the numerator, I've got to use the product rule. I've got x times 3 to the x power. So I've got to use the product rule. So that's going to be what? Take the x times the derivative of 3 to the x. Well, that's going to be 3 to the x times the natural log of 3. So that's x times the derivative of 3 to the x. And then plus 3 to the x times the derivative of x. Well, that's just 1. So that's our product rule on top. All right, let's then look at the bottom here. We're going to simplify this in just a second. The bottom, the derivative of 3 to the x is 3 to the x times the natural log of 3. The derivative of negative 1 is 0, so I'm not even going to write it. All right. Okay, let's see what we have up here. Let's see what happens here when we plug in 0 for x. Well, x here is going to give us a 0. 3 to the x is going to give us a 1, 3 to the 0 power. That's going to stay the ln of 3. 3 to the x is going to be 3 to the 0, which equals 1. So let's see what we have here in the numerator here. We're going to have 0 times these two expressions. So that's going to be 0 for that first term. This right here, the limit, because we've got that x there, that's going to give me a 0. Plus, now 3 to the 0 is 1. 1 times 1 is 1. So my numerator from doing the limit is going to be a 1. Now what's my limit when I do the denominator? 3 to the 0 power is 1 times ln of 3. So my denominator is going to be the ln of 3. So therefore my limit then is 1 over the natural log of 3 from L'Hopital's rule. Okay. All right. So I wanted to get some additional examples of that. Now what we're going to make on this, what I want to do next then are some other kinds of cases here. Here we've been looking at something divided by something and trying to get the limit, all right? Well, we can have problems in which, let's say, we can have something called an indeterminate product. Up to now, we've been looking at indeterminate quotients. Now we're going to look at products. So let's look at an example of what we're talking about here. Let's look at the limit as x approaches 0 from the positive side of x times the natural log of x. Well, let's just plug in the 0 plus into both of these. That just means we're approaching 0 from the positive direction. Well, this limit here, when I plug in 0 for x, that's going to be a 0. But does anybody remember then what the limit of the natural log is when I approach 0 from the positive direction? Negative infinity, yes. Times negative infinity. Remember that that log function, let me just draw a quick graph here. It goes like that, and then it goes down, 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 down. It goes to negative infinity as we approach 0 from that positive direction. So here we have something like 0 times infinity, or 0 times negative infinity. Well, what in the world is 0 times negative infinity going to be equal to? The question is the 0 going to win out? Is the infinity going to win out? Or by winning out, I mean, is the result going to end, the limit going to be infinity? Is the limit going to be 0? Meaning, is the 0 going to win the battle? Or is it going to be some finite number in between that might end up being the result? It can work in any of those three. So, this is what we have to do. We have to convert this quote-unquote indeterminate product into an indeterminate quotient. An indeterminate quotient. Okay. So by indeterminate quotient, then, we're talking about 0 over 0 or infinity over infinity. Plus or minus infinity over plus or minus infinity. Okay, so let's see here. There's always, pretty much always, either an easy way to rearrange this or a bad way to rearrange this. All right? Okay. We know that the ln of x goes to negative infinity when we go to 0 from the positive side. And we know its derivative is 1 over x. So it's a nice, simple derivative. Okay. Similarly, okay, x is a real simple derivative, but also if we put the x into the denominator, we're going to end up with an infinity over infinity. So let me show you this. X, ln of x, I can change to, let's keep the ln of x on top, but I can put that x in the denominator if I do it as a reciprocal. Like this, all right, algebra. Now, if we look at this then, as x goes to 0 from the plus side, this, of course, goes to negative infinity, the ln of x. And what happens here? What is 1 over x going to be heading to when x gets real smaller and smaller and smaller and smaller in the denominator? It'll be infinity. It'll be positive infinity. we're going to have 1 over 1/10, 1 over 1,000, 1 over 1 million, 1 over 1 over a million. It's going to be approaching positive infinity. Dividing by smaller and smaller numbers gives you a bigger and bigger result. So this is going to go to positive infinity. So by rewriting it like this, we now have a indeterminate quotient. An indeterminate quotient, negative infinity over infinity, and that means we can use the L'Hopital's rule. So we can use the rule. All right. So let's figure out what we get here. Let's see. So we're going to have here, now the limit, x is going to 0 from the positive side. We're going to be rewriting this as the ln of x in the numerator, and the denominator is now 1 over x. Okay, we know we can apply the rule. So let's do the derivative. The derivative of the natural log is 1 over x. And then for our denominator, the derivative of x to the negative 1 power is negative 1 times x to the negative 2, right? Negative 1 x to the negative 2. And then this is the limit as x goes to 0 from the positive side. So we're going to do some more algebra here, all right? We've got x to the minus 2 in the denominator. I can make that an x to the positive 2 if I put it in the numerator. So this is equal to the limit as x approaches 0 from the plus side. Let's bring, here's the minus sign. I'll bring that up. And then it's going to be 1 over x times 1 over x times x to the positive 2 power. All right? All right, well, that simplifies pretty easily, I hope. One of the x's cancels out. So this is the limit as x approaches 0 of minus, and then I can cancel an x out. So I'm left with just minus x. So, of course, that limit, as we put in 0 for x, our limit now is 0. Okay? So that's our answer. We had to convert it, though, first into a quotient that satisfies the conditions for the rule. All right. I'm going to do another indeterminate product, but before I go on, anything on this one that I just did? All right. Let's do this example then. The limit as x approaches pi of what? Okay, pi minus x in parentheses times the tangent of x divided by 2. All right, let's see what happens here. Well, when we plug in pi here, we get pi minus pi is 0. So that limit would be a 0. But when we plug in pi here, what's the tangent of pi over 2? What does that equal? Yeah, it's 1 over 0 or infinity. Okay, we can write it as infinity. The tangent of 90 degrees, remember tangent is sine over the cosine. Cosine of 90 degrees is the 0, so this tangent is equal to infinity. So we have a 0 times infinity case. Yes, Jen?
How did you get infinity from 0?
How did I get infinity from 0? Pi over 2.
1 over 0.
Okay, yeah. The tangent of pi over 2, okay, is 1 over 0. Well, we're approaching 0. The cosine is approaching 0. The sine is approaching 1. Again, we're dividing by smaller and smaller numbers. That's the same as getting bigger and bigger numbers. Make sense? Does that make sense?
Yeah, but we're not talking about zero. Yeah.
All right. Right. We're not actually dividing by zero. I'm talking about as we're getting closer and closer to zero. The numbers are getting smaller and smaller in the denominator, and so we're getting bigger and bigger. It's really another thing you should know is that the limit as we approach pi over 2 from the minus sign of the tangent is infinity. I mean, that's a basic fact from trigonometry that we should know. In fact, I believe that little fact is also in my formula sheet. All right? So, we have 0 times infinity here. It's on the last page. All right. So therefore, let's see if we can convert this to an indeterminate quotient. Convert to an indeterminate quotient so we can apply L'Hopital's rule. All right. Now, let's see. Any recommendations as to which one of those two expressions I should put in the numerator and which one I should convert into a denominator?
I would put x in the denominator.
Oh, you would. Okay, let's do it. Let's see what kind of mess we get. All right? Because remember I said there's generally a good way to do it and there's a not so good way. So let's check it out. Okay, so if we decide to put pi minus x in the denominator, how would I have to write that? Pi minus x to the negative 1 power, right? Because I'm converting it from the numerator to the denominator. And then we still have the tangent of x over 2 in the numerator. Okay, so this certainly goes to infinity. And this will actually also go to infinity as x goes to pi. But, so we could apply the rule, but it'll be a mess when we try to apply the rule. The derivative of the tangent is the secant squared of x over 2, and then we do the chain rule times 1/2. But then look what kind of a mess we end up down here. Let's see. I don't know if this is helpful here. We have minus 1. We have to do the times pi minus x to the negative 2 power. And then we use the chain rule, and we have to then multiply by a negative 1. Yes?
On the sheet, it says that it depends like which side you're
Yes?
from.
Absolutely. Whether it has a plus or a minus after the pi over 2.
This one, you said it was infinity, but how do we know it's not negative?
Okay, I should have put then here a plus. Yeah, should have put a plus there. Thank you.
It says that it
Oh, it should have been a minus. Sorry. Okay. Should have been a minus. All right. Let's see. What would this come out to be? Oh, I brought down the negative 1, and then I have a negative 1 from the chain rule, right? Because 2 negatives multiplied together gives you a positive. So I just changed the 2 negatives to a positive. That's all I did. Let's see, now the secant is 1 over the cosine. Let's see, so we've still got a problem. Well, let's see, as we go to pi over 2, as we go to 90 degrees, the secant is 1 over the cosine, right? So the cosine is going to what? What is the cosine of 90 degrees? 0. So we're going to 1 over 0 again. So we're still going to it. We're going to infinity. And then this thing down here is also going to infinity. So we would have to apply, it's a mess. It turns messy. We'd have to see if we could apply the rule again. And by this time, no, you don't even want to go there you've done it the wrong way. You put a big X through it, and you do it the other way. All right? Okay. So let's do it the other way, and things are much, much nicer. Let's bring the tangent down into the denominator. So this equals the limit as x approaches pi from the minus side of, we're going to keep that pi minus x up there in the numerator, but now I have to bring the tangent down into the denominator and have an equivalent expression. So what would be the function that I would be putting in the denominator? What's the reciprocal of the tangent function? Yes, it's cosine over sine, which is what function? Cotangent. So cotangent of pi over 2 would be in the denominator. Okay, now this, let's see what we have here. This gives this, of course, pi minus pi. That gives us a 0 there. Now, as you said, Jenna, the cotangent is the cosine over the sine. So as we go to, and this is pi over 2, so the cosine is going to go to 0. The sine of 90 degrees is 1. So the bottom is also going to go to 0. Yes.
Should it be the cotangent of x over 2 or pi over 2?
Oh, it should be x over 2. Yeah, thanks. Yes. Okay. I had already just decided to substitute it in, but thanks. All right, so again, so we have a 0 limit on top, a 0 limit on the bottom, so we can use the L'Hopital's rule. Let me put a capital H there to say we're going to use the rule. All right, so let's do the derivative of the top and the derivative of the bottom. Okay, the derivative of the top is easy. Derivative of pi minus x is negative 1. And the derivative of, what's the derivative of the cotangent function? It's negative cosecant times the cotangent. Negative cosecant of x over 2 times the cotangent of x over 2. So the derivative of the tangent is the secant squared. Oh, wait a minute. Did I? Whoa. Wait a minute. Yeah. It is. Just forget what I just wrote there. The derivative of the cotangent is the negative cosecant squared of x over 2. And then we have to use the chain rule. So the derivative of x over 2 is 1/2. All right. Okay. Now, this is going to be nice here. Okay, we've got a minus 1 on top, and then the cosecant of, when we put pi in for x, the cosecant of pi over 2, well, the cosecant is the opposite, is the reciprocal of the sine. Cosecant is 1 over the sine. So the sine of pi over 2 is 1. So the cosecant of pi over 2 is 1. Remember my tricky little crazy sounding thing that I used to remember? Cosecant starts with a hard sound and sine starts with a softer sound to remember that they're reciprocals of each other. Whatever works, all right? So this bottom part is negative cosecant squared of pi over 2 is going to end up being 1 times 1. And then we have, of course, don't forget, we have a 1/2 also over here. All right, so let's simplify this. The two minuses cancel each other out. So I have 1 over 1 divided by 1/2. And then dividing by 1/2 gives me 2 over 1, or 2. Okay, so that's my answer to this one. We can all see how that pesky little trigonometry course that we had to take prior to this is rearing its ugly head. Yeah.
How did you know, like, before you even worked it out, that way is much easier than the other?
Well, if you think, well, if I move the tangent down, I just have a cotangent, and that's a pretty easy derivative, minus cosecant squared. And the pi minus x is an easy derivative. Even if you started the other way like we did, it doesn't take you long with this, what we did up here. It doesn't take you long to figure out this is starting to look really ugly. All right? That's the way to put it. So stop that and go on and try the other way. I mean, that's what I can recommend. You start, nothing wrong with starting the wrong way. Just realize that this is leading to disaster and just do it the other way. Okay? All right. So this is indeterminate product. 0 times infinity, indeterminate product. Okay, let me just repeat that. Indeterminate product. Zero times infinity. All right. Okay. The next thing we look at then is another indeterminate type of thing. This is, let me put this up here for those folks. This is the indeterminate difference. Okay, so we have an indeterminate quotient. That was the Hopital's rule. We had an indeterminate product. Now the indeterminate difference. Indeterminate difference. And the indeterminate difference is going to be infinity minus infinity. What the heck is that? All right. So let's look at an example here. The limit as x approaches pi over 2 from the minus side, all right, of the following. The secant of x minus the tangent of x. All right. So let's see what we get here. The secant we know is 1 over the cosine. The cosine of pi over 2 is 0. So this right here is going to be an infinity at the limit. The tangent of pi, and we've just gone over that as we approach pi over 2 from the minus side, the tangent is the limit is infinity. And we have a minus in between. Let me, you know what? Let's just look at how this tangent function graphs here. Tangent of x. All right. Of course, at 0 radians, it's 0. It goes up, and I know this isn't the correct exact shape, but it goes up, and let's say this is pi over 2. It's approaching it from the minus side. And then on the other side, it's going to go down, and this is minus pi over 2. All right? Now, it repeats that same pattern then on the other side of positive pi over 2. So let's go here to pi. On the other side of, minus, that would be, pi, and this would be 3/2 pi, thank you. Okay, right here then, it's going to again be 0, the tangent of pi is 0, okay, it's the sine over the cosine, but here, it's on the other side of pi over 2, it's going to be going down to minus infinity, and then here, as we head up to 3/2 pi, it's going to go up to plus infinity. So you see right here, let's draw a little vertical line right here at pi over 2. From the left side, from pi over 2 with a minus in front of it, that's going to go to plus infinity. Over here, as we're heading to pi over 2 from the other side, it's going to go to negative infinity. Does that help a little bit with just kind of refreshing what that tangent graph looks like? Okay. All right. Here, let's get back here to this problem then. Okay, so we have this infinity minus infinity thing. Well, this is the deal, what we want to try to do with these indeterminate differences. We want to try to rewrite the expression as either a product or a quotient. As either a product or quotient. Okay. So let me just put, so what our expression here is secant of x minus tangent of x. Well, let's put these in terms of sine and cosine, okay? The secant is 1 over the cosine of x minus, now the tangent is the sine over the cosine. So, we very conveniently have the same denominator here, so I can represent this over a single denominator of the cosine of x, and the numerator then will be the 1 minus the sine of x. So that's how I'm going to rewrite our expression with the numerator and denominator. Okay, so let's see what we get here with this. Because we want to see, well, are we able to apply L'Hopital's rule, and we will. So therefore, we're going to have, this is the limit as x approaches pi over 2 from the minus side of, now it's going to be 1 minus the sine of x all over the cosine of x. All right. We'll take a break after this one. So the cosine of pi over 2, that's heading to 0. The sine of pi over 2 is 1, so 1 minus 1 is also heading to 0. So we now have a 0 over 0 case, so we can do the rule. All right. Okay, so let's do the derivatives then. This is the limit as x approaches pi over 2 from the minus side. Okay, the derivative of 1 is 0. The derivative of the minus sign is the minus cosine. And then the derivative of the cosine is the negative sign. Okay, let's see what we have here now. All right. Now, the cosine of pi over 2 is 0, so this goes to 0. The sine of pi over 2 is a 1, so this bottom part goes to negative 1. So basically, this limit then is going to be 0 on top, divided by negative 1. Well, 0 divided by any non-zero number is equal to 0. So that's our limit using the rule. Okay. All right. Let's take a 5-minute break then to 5 after. And remember, to please turn in homework number 2. If you need a stapler, here's a stapler. What's that? You have to go to. Oh, yeah, I know.
I didn't realize that I had already. I'm like, I'm not rewriting.
Well, don't throw it. Don't just use this and then get the other time.
All right.
Yeah.
Thank you.
Oh no, what's going on? Are we out of staples? Or got jammed? You get extra points, Jenna, for fixing the stapler.
Hey,
I'm gonna need.
I was going to, I was gonna pull it out.
Well,
I'm not sure if you're, I was working on it. Nothing really looks like that.
okay. I think that one is going to be
I like that.
it's going to be a hyperbolic, I believe. Let's look at our sheet here. Like that? Yeah, it's going to be the cinch inverse, where we've got the x squared and the 1. So this is how you're going to, I'll get you started on it, okay? So, give me the problem. Okay. Now, let's just put up here, the formula here, the integral of 1 over square root of 1 plus x squared dx is the cinch inverse. Okay? All right. Yeah. So we're going to have to do a substitution here. Okay. We want to get it over into the form that looks like this. So why don't we have this? Let's have u equal to 2x, right? So that when we square it, we get the 4x squared. So now, we're going to only have a u squared plus 1 in there. Now let's see what else. So if u is 2x, then du is 2 times dx. Or in other words, 1/2 du is equal to dx. So I'll just show how it gets converted, and then you can go from there. So we have a 1/2 du, and then over here, this converts to 1 over the square root of u squared plus 1, and we can use our formula over there.
Okay.
Are we all in agreement with that? Oh, yes. With it being moved forward.
Yes, I already did set up times downstairs with her.
Okay. Did you have a question? Well, you thought it was due today. Then go ahead and just turn it in.
Yeah.
You did all that already.
Yeah.
Show off.
Oh my God, how many hours does that take?
Okay, let's see what we got here. All right.
4 hours down.
Date of the test now is going to be infamous 9/11. Okay. Time allowed, well, in class, 2 hours. Okay, so, you can use scientific calculator, 6 function, just not a graphing. Okay?
She knows.
Okay, perfect. All right. I'm going to send, I put it down in the mailbox.
Okay.
So we'll put by instructor. And let me put my signature here. Oh, let's see. What's today? Thank you so much. And then I'll put my cell number here. Okay. If you then...
I'll take it down to her.
Okay.
I will
Very
do.
good. All right. Got it.
Sorry.
Yes, I have something.
You have to leave it.
Okay.
Oh, okay.
Well, I'll get the rest of it. Is there anything else I can get out?
Yes, the nothing more about the notes, in fact, they're already, the scan notes are already.
Thank you.
All right. So we've done indeterminate quotients, that's the L'Hopital's rule. We've done indeterminate products, indeterminate differences. The final thing we have is indeterminate powers. All right, and this is probably the most challenging of the lot.
Hold on, do you have any of those?
Hmm?
Do you ever have additions?
No. Infinity plus infinity is infinity. Right? If something is really big plus something that's really, really big, it's going to be really, really big. It's only when you have the difference, infinity take away infinity, that things can get screwy. All right. So what we're talking about here is the limit, as x approaches a, of some function f of x taken to the power g of x. So we're talking about, so our two functions now, one is the exponent of the other. Okay. Now, there are three types of indeterminate powers. There is zero when the f function is going to zero and the g function is going to zero. So there's the 0 to the 0 case. Then there is the infinity to the 0 case, where the f is going to infinity and the top function is going to 0. And then finally there's the 1 to the infinity case, where the bottom function is going to 1 and the power is going to infinity. Basically, it's easier to explain these bottom two. 0 to the 0 is, well, I guess you can just say 0 to the 0, what the heck is that? So let's just leave it at that, but that would make it an indeterminate case. If we have something that's getting really, really large, and we're taking it to a really, really small power, we really don't know what's happening. Similarly, even when something is going to the number 1, and we're raising it to a really, really large power, we're still not quite sure if that's going to be just 1 or if it's going to be infinity. We don't really know. So that's why we have these three types. Now, what we do is this. We use natural log ln to convert the expression to a 0 times infinity type product. All right, so we're going to convert it to a product by using the natural log. All right, so the best way is just showing with example here what we're talking about. Let's look at the limit as x approaches 0 from the plus side of 1 plus the sine of 4x, close parentheses, raised to the cotangent of x power. Ugh, all right. Okay. Now, when x goes to 0, the sine goes to 0. So 1 plus the sine, that's going to go to 1. Now, the cotangent is what? It's the cosine over the sine. So when sine goes to 0, we have a 0 in the bottom. Cosine goes to 1. So this goes to infinity. So what this means is this is a 1 to the infinity type. Right. All right. How do we handle this? Well, let's do it this way. Let's designate our expression that we're taking the limit at. Let's just use the variable y. So let y equal 1 plus the sine of 4x, close parentheses, to the cotangent of x. So that's what we're calling y. Now what we're going to do is take the natural log of both sides. Take the ln of both sides. Okay, so the left-hand side becomes the ln of y equals the ln of 1 plus the sine of 4x raised to the cotangent of x power. But remember with the log property, if I have a power here, I can bring it out front. So this equals the cotangent of x times the natural log of 1 plus the sine of 4x. Are we okay so far with this? Okay, what happens here when x goes to 0? Well, the cotangent of 0 is, let's see, cotangent of 0 is going to be, goes to infinity, right? It's cosine over sine. And then when this goes, when x goes to 0, this is going to, sine of 4x is going to go to 0. So 1 plus the sine of 4x goes to 1. And what's the ln of the number 1? 0. Yes. So this thing goes to 0. So this is now an expression which is the 0 times infinity case. All right. So therefore, let's work with it then as that. All right. Okay. Now, I need to then, so we have an indeterminate product. So we want to convert that to an indeterminate quotient. And we want to do it the easier way. Convert to indeterminate quotient. All right. Okay, so what are we working with here? We have cotangent of x times natural log of 1 plus the sine of 4x. And we want to represent this as a quotient that fits L'Hopital's rule. Yeah, Jenna? Very good. That's exactly the way to do it. Let's keep the ln on top, because if you work it out, and I won't go through the torture of the other way, but the other way will rapidly look ugly. Keep the ln on top. If we want to put the cotangent expression in the denominator, we have to make it into the tangent. All right. Okay, so let's see what happens here. Let's look then at the limit as x approaches 0 from the plus side of this quotient. ln of 1 plus sine of 4x all over the tangent of x. Okay, well the tangent approaches 0 as x approaches 0, so that bottom one is going to approach 0. And let's see here, the top one, that's going to approach 0. The ln of 1 is going to approach, is going to be 0. So we have a 0 over 0 case. So we can use the rule. All right. So let's do the derivative of the top over the derivative of the bottom. Limit as x approaches 0 from the plus side. Okay. Now, the derivative of the natural log, oops, let's go up here. Derivative of the natural log function. All right. It's basically the derivative of the inside function divided by the inside function. That's the general rule. So the derivative of 1 plus the sine of 4x is going to be 4 times the cosine of 4x, right? Using the chain rule. And then over 1 plus the sine of 4x. So that expression there is the derivative of the natural log that's on top. Okay. Now the derivative of, on the bottom, the derivative of the tangent is the secant squared. All right, let's see if this has benefited us in any way. Now let's plug in that 0 and see what kind of numbers we get. Well, the cosine of 0 is 1. So this is going to become 4 times 1 right there, over. Now we have a 1 plus the sine of 0, which is 1 plus 0. So we have a 1 there. So that's where our top expression heads towards. Now, the secant squared is, of course, 1 over the cosine squared. And the cosine of 0 is 1. So the secant squared is 1 times 1, or 1. So we have 4 divided by 1. Our limit is the number 4. Yeah? Oh. Okay, I haven't finished yet. This is not the final answer. I got so excited about finding that 4. All right, so let me actually finish that thought. This is not the final answer. Okay, let's go back up to what Jenna was talking about the fact that we had the ln. This is what we have. The ln of, so this whole thing is actually the ln of y approaches the number 4. Because way back up here, we had taken the expression that we worked with is equal to the ln of y. So the ln of y approaches the number 4. All right, but we want to find out, what does y head to? Okay, because y is our expression. Okay, now remember this, that y can be written like this. Y is e to the ln of y power. Remember, the exponent and the natural log are inverses of each other. So I can write y as the e to the ln of y power. Well, we know that the ln of y is approaching 4. So therefore, since the ln of y approaches 4, then y approaches e to the 4th power. Since y, our expression that we're looking for, the limit, it can be written as e to the natural log. We have found that our natural log heads to 4. Therefore, our y heads to e to the 4th power. Does that make sense? You just use the base e. It might help after we do get another example with this. This identity here is because the exponent function and the ln are inverses of each other. So e to the natural log of y just takes us back to y. So I can then write my original expression as e to the natural log of y. We know that we have just found out that the natural log of y heads to the number 4. So therefore, our original expression heads to e to the 4th power. Okay, let's do another one, and hopefully that'll start to look more familiar. All right, let's look at, for this next one, the limit. We're going to do this and one more. The limit as x approaches 0 of the following: 3e times e to the negative x power minus 2, all raised to 1 over 6x. All right. So when x goes to 0, 1 over 6x goes to infinity, because x gets smaller and smaller. Now what happens here? When x goes to 0, we have 3 times e to the minus 0 power minus 2, but this is 3 times 1, take away 2, so that expression approaches 1, 3 minus 2. So what we have here is a 1 to infinity case. All right. So that's our second kind of indeterminate case here. So let's do the natural log. So let's do it this way. Let y equal, in parentheses, 3e to the negative x minus 2 to the 1 over 6x power, and take the natural log. So the ln of y is equal to the ln of 3e to the minus x minus 2 to the 1 over 6 power, and I use my rule of exponents, my rule of logs. I carry down the 1 over 6x, so it's equal to 1 over 6x times the natural log of 3e to the minus x minus 2. So that's what the natural log of y equals. Now we want to see, and remember, x is approaching 0. All right, so what do we have here? If x is approaching 0, 1 over 6x, well, that still approaches infinity. When x approaches 0, this inside expression approaches 3 minus 2, e to the 0 power is 1, which is equal to 1. And we know that the ln of 1 is equal to 0. So we have here, this turns into a 0 times, an infinity times 0 case, which is what we want. All right. Okay. Now, let's convert this then into a indeterminate quotient. So convert to an indeterminate quotient. All right. Let's see. We could, so we have a couple of options here. One of our options is to, notice we actually already have if you look at this, we actually already have a numerator and a denominator kind of already built in here. 1 over the 6x can be our denominator, and the ln can be our numerator. All right, and that is the case that'll work out best for you. So let's do this then. So therefore, we're going to then write this as the ln of 3e to the minus x minus 2 in parentheses over 6x. And this, of course, is the limit as x goes to 0. All right. So what happens here? We have 6 times 0, so the bottom goes to 0. And then the top, well, e to the 0 power is 1. 3 minus 2 is 1. The ln of 1 is also 0. So the top also goes to 0. So this quotient is a proper indeterminate quotient of 0 over 0. So we can use the rule. So let's do the derivative. The bottom one is certainly an easy derivative, so that's a hint you're on the right direction. The derivative of 6x is just 6. The top we have to do a little bit of work on here. Again, remember that the natural log derivative is the derivative of the inside function divided by the inside function. So this is going to be what? Derivative of derivative of 3e to the minus x minus 2. That's going to be 3e to the minus x times minus 1 with the chain rule. The minus 2 goes to 0. And then it's divided by just the function on the inside, 3 to the minus x minus 2. All right. Okay, let's clean this up a little bit and see what we've got. So this is the limit as x approaches 0 of 6 in the denominator. In the numerator we have, let's bring the minus over, we have minus 3 e to the minus x over 3e to the minus x minus 2. All right. Okay. All right, let's see what happens now when we plug in 0 for x. And it'll work out nicely. Okay, we're going to have here minus 3 e to the minus 0 over 3e to the minus 0 power minus 2. That's our numerator, all over 6. So that's going to be minus 3 over 3 minus 2, all over 6. And so that's minus 3 over 2 divided by, minus 2, over 1. That's minus 3 over 1 divided by 6. That's negative 3 over 6, negative 1/2. So that's our limit. Now this minus 1/2, this is the natural log of y is approaching minus 1/2. So we want to know what y is approaching. Y will be approaching e to the minus 1/2 power, using the same argument as before. Just remember, this is the natural log limit, so to get the original expression, it's e to the minus 1/2. And it's all based on the fact that the ln of y is equal to that y is equal to e to the natural log of y. All right. This is going to minus 1/2, so our y is going to e to the minus 1/2 power. Yes?
So our answers for consumer cars are generally going to be e to whatever.
Yes, right. In other words, whatever we get for the natural log limit, our actual answer here is going to be e to that limit. Is that what you're saying?
Yeah.
That's exactly correct. Right? All right. And one more indeterminate product. Remember, we have 3 cases here. We had so far we've looked at let's see, what did we looked at, we've looked at the 0 to the 0 case, we've looked at the infinity to the 0 case. Now, I think that's what we looked at. No, yeah. 0 to infinity. We did one. The first one was 1 to infinity, and then we looked at. No, that was the second. Yeah. They were both 1 to infinity. Right. Mm-hmm. Both 1 to infinity. We're now going to look at 0 to the 0 power. 0 to 0. All right. Okay. Okay, so let's look at the limit then. Let's get all this over here. Of the following. As x approaches 0 from the plus side, of e to the x minus 1, close parentheses, taken to the x power. All right. So let's see. This is obviously going to go to 0, and then this is 1 minus 1. E to the 0 is 1. So this is going to be 0 to the 0 power. So that's the type we were working with. So let's take the natural log, and let's do it this way. Let y equal to our expression, e to the x minus 1 raised to the x power, and now take the natural log. ln of y, I'm just going to bring this down right away because we know that's how it's going to work, equals x times the natural log of e to the x minus 1. All right. Now let's see what happens here when we have, let's look at the limit as x approaches 0 from the plus side of this new expression and see what kind it is. Well, obviously x is going to be approaching 0, and e to the x minus 1 is going to be 1 minus 1 is 0 from the plus side. So as we're taking the natural log, as x goes to 0 from the plus side, the natural log goes to minus infinity. So this is, again, is 0 times infinity product. So let's convert it to an indeterminate quotient. All right. So let's see here. Which one do we want to have? So ln of y, we want to have something over something. Yeah, I think that'll work out better. So let's put the x on the bottom. Let's see how that works. So to transfer x to the bottom, to the denominator, how do I need to write it in the denominator then? 1 over x, the reciprocal. And then the top number then is just, the top expression is just going to be the ln of e to the x minus 1. Okay, so let's take this limit as x goes to 0 on the plus side. And that's going to be of the ln of e to the x minus 1 over 1 over x. Let's see, as x goes to 0, 1 over x is going to go to infinity. And then here, as x goes to 0, that's going to be 1 minus 1. That's going to approach 0 from the plus side, 1 minus 1. And the ln of, as x approaches 0 from the plus side, is negative infinity. So we've converted it into a infinity over infinity case. Okay, so let's use the rule. So it's going to equal the limit as x goes to 0. Let's do the derivatives here. Let's do the derivative first of the top part. Again, it's going to be the derivative of the inside expression. Susan, you got a question? No. Derivative of the inside expression, which is just going to be e to the x over the entire inside expression. So that's the derivative of the ln. And then the derivative of 1 over x is going to be minus 1 over x squared when we do that derivative. Okay. Well, let's see if this has helped us out any. What would you like to do next here to see whether this has helped out? Yeah. Well, okay. Let's look at the derivative of 1 over x. That's the derivative of x to the minus 1 power, right? Bring down the minus 1. Reduce your exponent to a negative 2. So I'm just putting it in the denominator as a positive x squared. Okay? So notice here we've got a fraction expression divided by a fraction expression. What might I want to do here to see how this limit is going to end up looking? What's that now? Well, yeah, bring the bottom expression up as a reciprocal. Get it out of the denominator. All right. We'll see if this works. I think we're still going to have problems here with this. But let's see what we get. Okay, this is going to be e to the x over e to the x minus 1 times, now bringing that up, that's going to be a minus x squared over 1. Because I'm just bringing it up out of the denominator. So this gives me a minus x squared. All right, this is tricky. Okay, let's just do this. Gives us a minus x squared times e to the x over e to the x minus 1. All right. Okay, let's see. When x goes to 0, what do we have here with this? We have this goes to 0, this goes to 1, so our numerator becomes 0, and then this becomes 1 minus 1, that becomes 0 also. So we are going to have to repeat L'Hopital's rule here, because we still have, when we do the limit, we still have a 0 over 0. So that occasionally happens. You have to repeat the rule. Now this is a trick that you may not necessarily immediately see that can be helpful here. What I ended up with here is minus x squared times e to the x over e to the x minus 1. All right. I can write that even a little bit more differently in order to be able to use the rule. I can write this as minus x squared over the reciprocal of e to the x over e to the x minus 1. So I'm now putting in the denominator e to the x over e to the x minus 1. So there's involved some tricky algebra here. I'm taking this, putting it in a denominator, but I have, e to the x minus 1 over e to the x. I have to do the reciprocal. All right. Okay. Now, I still have to use L'Hopital's rule. This gives me a 0. This also gives me 1 minus 1 is 0. 0 over 1 is 0. This is still a 0 over 0 case. But this turns out nicer. I have minus x squared. Let's simplify this part right down here. E to the x minus 1 divided by e to the x. I can basically separate this out as e to the x over e to the x minus 1 over e to the x. So I'm going to get a nice, much easier expression. E to the x over e to the x is 1 minus 1 over e to the x. And of course, another way of writing 1 over e to the x is minus x squared over 1 minus e to the minus x. So there's a lot of tricky algebra. I'm just converting it, bringing the exponent out of a denominator and changing the sign. Again, this is still a 0 over 0 case. But now do the derivatives, and we have easy derivatives to do. Now use the rule again. So I get, for the derivative on top, I get minus 2x, easy derivative. On the bottom, and so this is the limit as x goes to 0. On the bottom, the 1 goes to 0, And the derivative, what's the derivative of minus e to the minus x? Yeah, right. Negative e to the minus x times chain rule -1. The two minuses cancel out, so I have positive e to the minus x. That's my derivative of the bottom. So therefore, e to the minus x there. All right, now we have a nice, let's see what happens now when we plug in 0. Well, 2 minus 2 times 0, that's going to be a 0. But down here, e to the minus 0, I'm going to get a nice 1 in my denominator. So this limit then is 0 divided by 1, which of course is 0. This was a mess, I grant you. This was a lot of manipulation to get to doable derivatives. So there's a lot of algebra involved here with this manipulation. All right, so therefore this means that the ln of y approaches 0 as x approaches 0 from the positive side. So therefore, what does our original expression, what is it going to be approaching? E to the 0. So y is going to be approaching e to the 0 power, and what does e to the 0 power equal? 1, right? That is our answer then. After all is said and done, we get a 1 as our answer, okay? That was the trickiest of the lot. I don't think you're going to have something quite that tricky on the in-class test. I didn't know how long this would take. I was actually hoping to be able just to have some time after all this was done to just do a couple of the practice problems on the review. But we still actually have, well, maybe I can do one of them. Will you throw rocks at me if I do one of them? Something from the practice set, just something. You know that practice set? This thing right here? I think to get to a different kind of thing here, I was going to look at, say, number 16, if you guys have got that there. Because this is something we haven't looked at recently, at least. We have this is on the practice set, we have f of x is equal to 3 plus the natural log of x taken to the sine of x power. And we're asked to get the derivative. And on the test, you will be told or hinted at that you should use logarithmic differentiation, all right? So the thing is, let's do the natural log of both sides. So we have ln of f of x on the left side. And then using the log rules, I'm just going to do this in one fell swoop. We bring down our sine of x times the natural log of 3 plus the ln of x. Okay? All right. Now, we then do the derivatives, do implicit derivatives, implicit differentiation. Okay, so the derivative of the ln of ln of f, that's going to be 1 over f times the derivative of the inside function. In other words, this is our inside function here. It's the derivative of that inside function divided by the inside function itself. So on the left side, I get 1 over the f of x times the derivative of f of x. And then I have to, on this side, I have to use the product rule. I have two functions here. So let's start it out with, say, let's take the sine of x and do the derivative of 3 plus the ln of x. Okay. that's going to be what? We're going to have 3 plus the ln of x on the bottom, and on the top, we're going to basically have, what? Well, what's the derivative of 3 is 0. The derivative of the natural log is 1 over x. So that's our derivative of the natural log. Then let's do the second part of the product rule. We take the derivative of the sine function, which is the cosine of x, and we multiply that by the second function, 3 plus the natural log of x. All right. So we get that. All right. Then basically, we want to get f prime of x. Well, f prime of x is going to, if we multiply both sides of this by f of x, multiply both sides by f of x, then on the left side, we do just have f prime of x equaling f of x times that whole thing that we have on the right-hand side. Let's clean up this first one a little bit. This would be sine of x in the numerator, and then I could put that x down in the denominator, x times 3 plus the natural log of x. Just do a little cleaning up of that expression. Plus the cosine of x times the natural log of 3 plus the ln of x. So I'm just rewriting that whole thing that I already had on the right-hand side. Now, this is okay for an answer, I suppose, but what I really want to see then is let's replace this f of x by what we are told it was originally. So f of x here, I'm just going to replace it with 3 plus the ln of x raised to the sine of x power, and then times that whole thing that I have in the bracket. All right, and then that's the final good answer then for the derivative. So at least I was able to go over one of these. Most of these derivatives require several uses of the chain rule. Did you have a question? Okay. And then the integrals require either the sine inverse or maybe a hyperbolic sinh inverse. So, and the back here has several examples of L'Hopital's rule, all right, for you to use. A couple of them you don't need to use L'Hopital's rule for, all right. Anyway, that's going to be good practice in addition to doing the homework and the take-home quiz to get you prepared. So on Monday, we're just going to start, we are going to do this section 7.1, not going to be on this test, it will be on the next test. It's on integration by parts. You may or may not ever have heard of that. So we might be venturing now into some new territory for some of you guys. All right, integration by parts. Wednesday, the whole period for the test, and then Friday we'll be back to new material now. Okay, thank you. Everybody turning in the homework that's turning in the homework. Thanks, Daniel. All right.
be worried where to go, it's like,
He was,